Refrigeration Principles and Cycles. Hello folks, welcome to today's lesson on refrigeration principles and cycles. Refrigeration is based on the principle of removing heat from a designated area and discharging it elsewhere. The basic thermodynamic process involved in refrigeration is the refrigeration cycle. The most common type of refrigeration cycle is the vapor compression cycle, which includes several key stages. Compression: refrigerant gas is compressed by a compressor, increasing its temperature and pressure. Condensation: the hot, high-pressure refrigerant gas moves to the condenser, where it releases heat to the surrounding environment and turns into a liquid state. Expansion: the liquid refrigerant passes through an expansion valve or capillary tube, causing it to expand, decrease in pressure, and cool rapidly. Evaporation: in the evaporator, the cold, low-pressure refrigerant absorbs heat from the area to be cooled, thereby evaporating back into a gas state. This cycle continues to repeat, effectively maintaining a constant cooling effect, components, and accessories. The efficiency and functionality of a refrigeration system depend largely on its components and accessories. Key components include compressor, the heart of the refrigeration system, responsible for compressing the refrigerant and moving it through the system. Condenser, a heat exchanger that removes heat from the refrigerant and condenses it into a liquid. Expansion valve regulates the flow of refrigerant into the evaporator, allowing it to expand and cool. Evaporator absorbs heat from the space to be cooled, causing the refrigerant to evaporate. Additional accessories enhance system performance and include filter dryer, removes moisture and impurities from the refrigerant to prevent system contamination. Accumulator stores excess refrigerant to prevent overflow into the compressor. Receiver acts as a reservoir for stored refrigerant in the liquid stage. Sight glass allows technicians to observe the refrigerant's condition and flow. System design and installation. When designing and installing a refrigeration system, several considerations should be taken into account to ensure optimal performance and efficiency. Load calculation: determine the cooling load requirements to adequately size the system and choose appropriate components. Layout planning: design an efficient layout for components and piping to minimize energy consumption and facilitate maintenance. Component selection: choose high-quality components that match the desired capacity and efficiency of the system. Installation practices: ensure proper installation techniques, including securing connections, insulating pipes, and leak testing. System balancing: adjust refrigerant charge and control settings for optimal operational efficiency and reliability. Understanding the fundamentals of refrigeration is essential for anyone involved in the design, installation, or maintenance of these systems. By grasping the principles, components, and best practices, professionals can ensure reliable and efficient refrigeration systems that meet the needs of modern applications. Refrigeration forms a critical part of both residential and commercial infrastructure, making it important for employees in this industry to maintain a comprehensive understanding of its fundamentals. 3. Air conditioning fundamentals, air conditioning principles and cycles, components and accessories, system design and installation. Air conditioning fundamentals. Air conditioning, often abbreviated as AC or AC, is the process of removing heat and moisture from the interior of an occupied space to improve the comfort of the occupants. This system can be used in both domestic and commercial environments. Air conditioning is widely used in buildings and vehicles. Here's a summary of refrigeration principles and cycles. Refrigeration principles. 1. Heat transfer. Refrigeration involves the transfer of heat from one location to another. 2. Thermodynamic properties. Refrigeration relies on the thermodynamic properties of fluids such as temperature, pressure, and entropy. 3. Refrigerant. A refrigerant is a substance that changes state liquid to gas and vice versa at low temperatures, allowing it to absorb and release heat. Refrigeration cycles. 1. Vapor compression cycle, the most common refrigeration cycle, which involves the compression, condensation, expansion, and evaporation of a refrigerant. 2. Absorption cycle, a cycle that uses heat energy to drive the refrigeration process rather than mechanical energy. 3. Evaporative cycle, a cycle that uses the evaporation of a liquid to cool the surrounding air. Key components. 1. Compressor, compresses the refrigerant, raising its temperature and pressure. 2. Condenser, cools the compressed refrigerant, causing it to condense into a liquid. 3. Expansion valve reduces the pressure of the refrigerant, allowing it to expand and become cold. 4. Evaporator allows the cold, low-pressure refrigerant to absorb heat from the surrounding air or water. Refrigeration cycle steps. 1. Compression. The refrigerant is compressed, raising its temperature and pressure. 2. Condensation. The compressed refrigerant is cooled, causing it to condense into a liquid. 3. Expansion. The pressure of the refrigerant is reduced, allowing it to expand and become cold. 4. Evaporation. The cold, low-pressure refrigerant absorbs heat from the surrounding air or water, causing it to evaporate into a gas. Types of refrigeration systems. 1. Air conditioning, systems that control temperature, humidity, and air quality in buildings. 2. Refrigeration, systems that cool products or materials to low temperatures. 3. Chiller systems, systems that use a refrigerant to cool water or air for use in air conditioning or refrigeration applications. Executive summary. Here's a summary of the components and accessories of a refrigerator. Major components. 1. Compressor, compresses the refrigerant, raising its temperature and pressure. 2. Condenser coils, cools the compressed refrigerant, causing it to condense into a liquid. 3. Expansion valve reduces the pressure of the refrigerant, allowing it to expand and become cold. 4. Evaporator coils allows the cold, low-pressure refrigerant to absorb heat from the surrounding air. 5. Insulation reduces heat transfer between the cold interior and the warm exterior. Electrical components. 1. Motor, powers the compressor and fan motors. 2. Fan motors, circulates air over the condenser and evaporator coils. 3. Relays, controls the compressor and fan motors. 4. Thermostat, regulates the temperature inside the refrigerator. Accessories. 1. Shelves, provides storage space for food and drinks. 2. Drawers, offers additional storage space for fruits, vegetables, and meats. 3. Door seals, ensures a tight seal between the door and the refrigerator cabinet. 4. Ice maker, automatically makes ice cubes. 5. Water dispenser, provides a convenient source of chilled water. Other components. 1. Refrigerant, the substance that changes state liquid to gas and vice versa to absorb and release heat. 2. Capillary tubes, regulates the flow of refrigerant into the evaporator coils. 3. Defrost timer, controls the defrost cycle to prevent ice buildup on the evaporator coils. 4. Drainage system, collects and drains condensate water from the defrost cycle. Here's a summary of refrigerator system design and installation. Design considerations. 1. Load calculation, determine the required cooling capacity based on factors like room size, insulation, and desired temperature. 2. Refrigerant selection, choose a suitable refrigerant considering factors like efficiency, safety, and environmental impact. 3. Compressor selection, select a compressor that matches the required cooling capacity and operates within the desired temperature range. 4. Condenser coil design. Design the condenser coil to ensure efficient heat rejection and minimize pressure drop. 5. Evaporator coil design. Design the evaporator coil to ensure efficient heat absorption and minimize pressure drop. Installation considerations. 1. Location. Install the refrigerator in a well-ventilated area away from direct sunlight and heat sources. 2. Leveling, ensure the refrigerator is properly leveled to prevent uneven cooling and reduce energy consumption. 3. Connections connect the refrigerator to a suitable power source and ensure all electrical connections are secure. 4. Refrigerant charging. Charge the system with the recommended amount of refrigerant to ensure optimal performance. 5. Leak testing. Perform leak testing to ensure the system is leak-free and operating efficiently. System components installation. 1. Compressor installation. Install the compressor in a well-ventilated area, ensuring proper mounting and connections. 2. Condenser coil installation. Install the condenser coil in a location that ensures efficient heat rejection. 3. Evaporator coil installation. Install the evaporator coil in a location that ensures efficient heat absorption. 4. Expansion valve installation. Install the expansion valve in a location that ensures proper refrigerant flow. 5. Capillary tube installation. Install the capillary tube to regulate refrigerant flow. Safety considerations. 1. Electrical safety. Ensure all electrical connections are secure and meet safety standards. 2. Refrigerant handling. Handle refrigerants with care, following proper safety procedures. 3. System pressure. Ensure the system operates within safe pressure limits. 4. Leak detection. Install leak detection systems to alert of potential refrigerant leaks. Testing and commissioning. 1. System testing. Test the system to ensure it operates efficiently and effectively. 2. Leak testing. Perform leak testing to ensure the system is leak-free. 3. Performance verification. Verify the system's performance meets design specifications. 4. Safety checks. Perform safety checks to ensure the system operates safely. In conclusion, refrigeration principles and cycles are crucial for understanding how refrigeration systems operate. The vapor compression cycle, absorption cycle, and evaporative cycle are the primary refrigeration cycles used in various applications. Key takeaways. 1. Refrigeration principles, heat transfer, thermodynamic properties, and refrigerant properties are essential for refrigeration. 2. Refrigeration cycles, vapor compression, absorption, and evaporative cycles are the primary refrigeration cycles. 3. Key components, compressor, condenser, expansion valve, and evaporator are critical components in refrigeration systems. 4. Energy efficiency, proper design, installation, and maintenance of refrigeration systems are vital for energy efficiency. 5. Safety considerations, refrigerant handling, electrical safety, and system pressure must be considered to ensure safe operation. Future developments. 1. Sustainable refrigerants, natural refrigerants, and alternative refrigerants will play a crucial role in reducing environmental impact. 2. Energy-efficient designs, advanced designs and technologies will focus on improving energy efficiency and reducing energy consumption. 3. Smart refrigeration, integration of IoT, AI, and automation will enhance refrigeration system performance, efficiency, and safety. Final thoughts: understanding refrigeration principles and cycles is essential for designing, installing, and maintaining efficient and safe refrigeration systems. As the demand for refrigeration continues to grow, it is crucial to focus on sustainable, energy-efficient, and smart refrigeration solutions. Thank you for taking this lesson today. We hope to see you next. Happy learning, folks!